So I would just like to finish off our discussion on the factoring algorithm. Are there any questions that you would like to ask me before we go ahead? So the circuit that we have so far built for the factoring algorithm is as follows. And today I will also give you another view of the factoring algorithm, which is based upon the quantum phase estimation subroutine. So far what we have is two registers. One is an m qubit register and the other is an n qubit register. And m is twice of n. And we started off, the first register started off in a big 0 state, and we created a Hadamard. We at a Hadamard gate act on all of these qubits, so we created an equal superposition of all states over here. And then at this stage we had a giant unitary transform. So this also started off in some state get 0, which is an n qubit state. This giant transform un is characterized or parameterized by this number a, which is chosen randomly and is bigger than 1 and smaller than capital N. And lo and behold, these m plus n channels emerge from this unitary operation. And we have defined this unitary operation to act in the following fashion. The unitary operator acting on two registers holding the integers x and y, and remembering that the first register is n qubit long and the second register is n qubit long. This leaves the first register unchanged and does a bitwise addition modulo 2 to the other register state with the state of the first register. That is, we get x addition modulo 2 with y. This is the new state, right? So this is where we started off our discussion with, right? So I hope I'm not missing anything out over here. Sorry. This is the Simon algorithm. So we have y addition modulo 2 with a raised to power x, and all of this is modulo n. Okay? So this is where we finish our discussion, and then we put a giant detector over here and we measured this state. This state turned out to be some z, some integer z, which is an n bit sequence going from 0 0, 0 1, 0 2 up to zn. And of course this has to be equal to a raised to power some r1, right? So this is the state that is produced after collapse. This is the new state that we get over here, and this collapses the first register into a particular state as well, and that state is kr plus r1, get with k goes from 0. One is the r, which is the order of the function ax mod n, right? So this is r. We don't know this r. We want to find out this r. And over, right? So this was our second kind of r R naught. And the third kind of R that we now see is R1. This R1. Because since this is a raised power some R1, if we measure the second register, this is going to collapse into an integer that can be expressed in this form, a raised power R1. Now this R1 could be anything. Of course, it's always less than R. R1 is always less than R, but R1 could be greater than this R0, or R1 could even be less than R0. So when we wrote the expansion in our previous lecture, the expansion of the state that we achieve at this point, this is the state. I do not know what we're calling the state. It could be psi 1 or psi 2. I think this is psi 2. Let's call it psi 2. Let me rewrite this state over here. Psi 2 is given by 1 over under root q. So I put the under root q here just for convenience. Okay, 0. A raised power 0, which is 1, plus ket 1, a raised power 1, plus ket 2, a raised power 2, r minus 1. Got it? This is the first row. And I'm just writing these rows in an amenable fashion. It's just a superposition, but I'm writing this in a manner so that it becomes easier to understand what is the state at that point in time. Then I have r minus 1, then I get r, one plus r plus 1, a1, all the way up to 2r minus 1, ar minus 1. Correct? And the third row, if such a row exists, 2r r minus 1, and this goes all the way. Finally, I will be left with c minus 1r where this c is q over r, the ceiling of this, plus c minus 1 r plus 1 a raised power 1 plus, and you might fall short of this, right? It's possible that if r is not some power of 2, you will not get all the terms in the last row, right? So you will get r naught terms in the last row perhaps. That's it. So this is the structure of the quantum state at the point 2, isn't it? Now when you do a measurement, you might collapse the second register into a raised power 0 or a raised power 1 or a raised power 2 or a raised power 3 or some a raised power r1, some r1. Now that r1 could be anything from 0 to this r. to this R minus 1. So that's why I write this R1 is less than R. So I can collapse onto any column of this array. So I can collapse onto this column, for example. Now the R that I get, let's call it R1. That R1 need not be the same as R0. It could be the same as R0, it could be less than R0, it could even be bigger than R0. Because if this R0 is less than R, you don't get all the terms in the last row, but it's possible that you get a term in a column that is beyond the last column of the last row. Right? So this is all over the place. In a sense, when you are projecting the second register into one of the exponents of A, you are picking up a particular column in this array, and the corresponding first register states would be of the form kr plus r1, where k goes from 0 all the way up to some c minus 1. So if you just look at the first register, just the first register, I'm not going to focus on the second register any longer because I'm not going to do anything with it. So if I just look at the first register, the state of the first register is a superposition kr plus r1, where this k goes from 0 to c minus 1. And I need to normalize, so I put square root c as well. And now I need to define my c. So previously I defined my c as the ceiling. Now I can define my c in two fashions. If my R1 is less than R0 or equal to R dot, then my C is defined as Q over R, the ceiling of this fraction, because I then have to take into account the last row as well. Because my R1 is within the last column. So the last entry here has an R0 in it, but my R1 is less than R0, so I do take into account the last column. So I need to go right down to the last row. That's why I put a ceiling sign here. And if my R1 is greater than R0, of course my R1 will always be smaller than R because of the periodicity of the function. But if my R1 is greater than R0, then I don't have the luxury of going to the last row of this array, because such an R1 doesn't exist in this last row. Therefore, I have to terminate before the last row, in the second last row. So in that case, my C would be defined as this floor, Q over R floor, which means the integer that is just lower than Q over R. Alright? So this is how my variable K varies from 0 to an upper bound C minus 1. Now at this point, the first register, my state is a superposition of these states. So I give you 2 minutes to just think about this, because this is really important that you understand this, and then we'll do the final step in this algorithm.
Get A with the associate. Get A is for something.
वो second register है ना, so I don't care about the second register any longer because I'm not going to do anything with it. It's separable, right? So the state is separable between the first and the second register, so I can look at one register independently from this point onwards. Before I had made a measurement, I had an entanglement. So now I collapse the entanglement by measuring one register, now I get certain states on the first register. And now I'm going to do something with the first register. In fact, if I actually don't need to do a measurement. If I just look at a subspace of an entangled system, exactly the same thing happens. And when we deal with density operator, this will become a bit more clear. Yes?
So you find that R not can be anywhere between 0 and R. What if it's 0? So R1 is less than 2.
When R0 is 0? R0 is 0 will happen when R is an exact power of 2. So all of the terms in a row will be present. Otherwise you fall short. Just look at a practical example. If in the example that we discussed yesterday, if my Q is 1024, that is I'm using 10 bits, 10 Q bits in the first register, and my R for a particular value of A is 6, then R does not divide Q, or Q is not a multiple of R, so you'll get a fraction as a result. But the number of rows in that prescription is always an integer. So what integer do I choose? Okay, so I think this Q over R in this case I think would be 170. So it's going to be, it's not going to be an integer but a fraction plus an integer. Anyway, so just look at practical examples if you want to get more meaning out of this. So now what do we do with the first register? Somehow we need to extract R out of it. We don't care about R1 because R1 is totally random. So you do a measurement on another run of an experiment, you initialize your qubits in the same initial state, you do another run. Since you are collapsing a superposition, it's possible that in the next experiment you get a different R1 and so on. Right? If you choose a different small a, you would still get a different R1. And in that case, you might even get a different R as well. So everything is random and probabilistic here. But we're not concerned about R1. What we want to find is R. Because R gives us some hope that we're able to find out the factors of capital N. Yes?
Sir, how is Z different from N?
How is
Z.
Z?
John used to define.
N is a number, right? N is some number, 15, 21, 39. N, capital N is a number.
Small.
Now small n is the number of qubits you would require to encode this capital N. Now this might be a non-integer, so you would use the integer that's just close to this fractional number, log capital N. This is how we define small n. So small n is the number of qubits, Z is the value of this qubit register after measurement. So this is, Z is some sequence of zeros and ones, and you can cast this in integer form as well. For example, if I have 2 qubits and I get Z could be 1, 0, right? First qubit, second qubit, or get Z is 1, 0. In integer form, this will be get 2. That's it. Sorry? No, that's not capital N. Capital N is just a number you would like to factorize. Capital N is a natural number, a composite number, an odd number that you would like to factorize. Okay.
सर बेसिकली उस कैपिटल एन को हमने फैक्टर्स करा के देन हमारे पास ये वैल्यू है ये भी
अभी हम फैक्टर ढूंढ रहे हैं ना उसके.
कैपिटल
So let's focus on the notation a little bit. N is a number, a natural number we wish to find the factors of. Small n is log of capital N and ceiling here. It's the number of qubits in the second register. M is the number of qubits in the first register. It's twice the number of qubits in the second register. And it turns out that this is equal to log of, another notation I've introduced is log of Q, or Q is a power of 2, which comes right after n squared. So this is our notation here. Alright? And C is an integer close to Q over R. K is a running variable, right? So you need to understand the notation. Anyway, let's move on. So what would we like to do with the first register over here? Any clues? We have a superposition and we would like to measure a superposition, which is difficult. So we would like to make this superposition go back to a computational state, to a sequence of zeros and ones. So how can we do that? First of all, we know that this is the state that I've written in the first register. Is this periodic? It's periodic. It has an order R. So it's going to repeat itself after some intervals, right? So, and we're going to draw this function as well in a minute. So what kind of operation do I need to map this back onto the computational basis? So like in any quantum interferometry experiment, you put in computational states, you create a superposition through a Hadamard, you do an operation, and then you need to get those wave functions back and re-interfere so that you get back onto the computational basis. You want an inverse Fourier transform, right? So at this stage, and from this point onwards, here, this point onwards, you would like to do an inverse Fourier transform. So let's call the state over here psi 3. And I'm just looking at the first register now. So what I need to do, what I need to compute is the inverse quantum Fourier transform of Kr plus R1. K goes from 0 to C minus 1, of course with some normalization factor, and C has been defined over here. Two kinds of C exist. So we already know what a Fourier transform looks like. Excuse me. So if I were to take an integer state, ket j, and find its Fourier transform, what would the output look like? It's going to be sum of k's, each k is being modulated by a factor ei 2 pi jk over capital N, where, and here k goes from j goes from 0 to n minus 1 square. This is how I define a quantum Fourier transform. Now the inverse of this, is really simple. If I were to take the inverse of ket k, the inverse Fourier transform of ket k would be a sum of all the ket j's, e minus I 2 pi j, this sign is switched, jk over n. Now my j is going from 0 to n minus 1, 1 over n to n. This is the definition of a Fourier transform, and you can actually see, and we've done this in class, that this is indeed the matrix that is formed from this definition is indeed the inverse of the matrix that is formed from these coefficients.
K is equal to 0.
Sorry?
Blue one.
This one?
K is equal to 0.
Sorry. Got it? So now we want to find out the inverse quantum Fourier transform of this variant of K. This is some K tilde perhaps. Let's see what it turns out to be. Can you do the algebra on your own? While I do it on my own. Psi 3 1 over under root C K is equal C minus 1 R. Okay, now this turns out to be 1 over under root C K 0 C minus 1, and then I would like to take this sum here, so I would just do ket j E minus I 2 pi j, this thing over here, kr plus r1. And how many terms do I have in the first register? No. M is the number of qubits. How many terms do I have?
C terms.
No. 2 raised power m. Right? 2 raised power m terms. Right? Or q terms. We've defined this as q. So I would put in q here, and I sum over all the j's from 0 to q minus 1, where q is 2 raised power m. Right? And I also need to normalize, and the number of terms is q. So this is my inverse quantum Fourier transform. So let me just do a bit of manipulation. I just want to change the order of the summation signs a little bit. I can just put the term that doesn't have a k in it, I can just bring it out. E minus I 2 pi j R1 over Q. Here I am left with E minus I 2 pi j KR over Q ket j. Now let's look at this term over here. What does this term look like? Can we find out the answer of the summation? This summation here, we have a sum of exponents.
It's a
Geometric series. Provided that J is not a multiple of Q over R. If J is a multiple of Q over R, then J R over Q is going to be an integer. And K is already an integer. So E I 2 pi in an integer will always give me 1. Right? And I have C terms of this kind. So the sum is going to be C. So this thing over here this summation could be if my Q over R divides J, which means that J is a multiple of Q over R, which is a compact form of saying this, of writing this, that J is a multiple of Q over R. If this thing is true, then the sum equals C. This sum equals C, because there are C terms here in the sum, and each term is 1, because e raised power I 2 pi into an integer is it's 1, and I have C terms of this kind, so the answer is C. Otherwise, I'll get a geometric series, and the sum of that geometric series I think is going to look like this: 1 minus e minus I 2 pi J R over Q, and how many terms do I have? C. That's the numerator. 1 minus, and the denominator will have pi J R over Q. This is when Q over R does not divide J. So this is a geometric series, right? So in which the ratio between two successive numbers is e raised to minus I 2 pi J R over Q. And I take the power with respect to the number of terms, and there are C such terms. So the power goes into the exponent. So if you like remembering formulas, I think this is the formula for a geometric series. 1 minus R, again we encounter R, so R is what's called the common ratio, I think. N is the number of terms. So this is the kind of formula that we have for a geometric series, I think, isn't it? So psi 3 could now be written in a nice, cozy, compact fashion as follows. Psi 3 equals C over Q so I get C here, don't I? C J power 1 this is the sum over all j's from 0 to q minus 1, provided j is divided by q over r, plus 1 over qc sum over all j's minus 1 in case that q over r does not divide j, e minus I 2 pi j r 1 over q multiplied by this thing, right? This ratio here. And if you look a bit carefully, this ratio is nothing but sine pi j r c over q divided by sine of pi j r over q. Okay. Of course, we get j as well. This is my final state. Now what is j? Ket j. What's ket j? What's j in this notation here? J are all the integer states. So the first register can collapse into one of the j states. It could be 0, 1, 2, 3, all the way up to q minus 1. Right? So I'm getting a state which is proportional to ket, which is proportional to ket j. So I'm getting some j as my output. Right? And that j could be anything. It can go from, so there's superposition of all j's from 0 to q minus 1. So I'm getting superposition as an output. I'm not getting a single j, but I'm getting superposition as an output. Alright? So now what I would like to do, how do I make sense of this? So any questions up to this point? Yes, please.
Why have you added the two cases when like q by r divide j and then it does not?
So when either this condition is met or this condition is met.
Yes.
So this summation is valid when q over r is not a divisor of j. So you take this term, then this term goes to 0. So this is a conditional summation. This summation will be operative when this condition is met. If this condition is met, this condition is not met. So this is just blanks out.
So there are some values of j such that the first condition is fulfilled, and there are some values.
Exactly, very nice. So there are some, so we don't know r as yet, by the way. We don't know r. But we do know q, because we know the number of q bits in the first register, but we don't know r. So j is a running variable from 0 to c minus 1. So some states will glow up in our output. Some states will not glow up. So let's see which states will actually glow up. Okay? And how do we find out? So now we're doing a measurement on the first register. And we're doing a measurement in the computational basis. So now we want to look at the first register. So when we do a collapse of the first register, what is our output going to look like? What state do we produce? Every measurement produces a new state. So when we look at the first register, what new state are we producing? So we're doing a measurement over here now. So now we would like to do a big measurement. Right? So these detectors are differentiating between ket 0 and ket 1, measuring in a computational basis. We're doing a big detection here. So our state over here, psi 3, is going to collapse into one eigenstate or one computational state. Ket, let's call it ket B. That ket B could be anything from 0 to c minus 1. So what we would now like to do is find out the probability distribution. So if we have psi 3 and we project onto a state ket B, we want to find out the probability, what this probability distribution looks like. This is what we need to do, don't we? Got it? So this is the probability that our output is an integer b. An integer b is something between 0 and q minus 1. It's really a sequence of bits that are produced. So the q bits become bits. The quantum bits become bits because now we went to the classical world. We made a measurement. So this is the probability that we are measuring a state b. Let's see what this state looks like. So if we take the projection of ket j with ket b, only the j with the b remains, right? Got it? So what I can actually do, instead of b I can also write ket j, but so my output is going to be c over q. Now this summation will become just one term, ket b here. I'll get ket b here. provided B is a multiple of Q over R. Right?
So how do we know this?
Right, we don't know as yet, but soon we will know. So let's, instead of using B, let's call this J prime. J prime. One of the J's. The J we're talking about is J prime. So the state is going to be E minus I. Now, okay, let's first minus I 2 pi J prime R 1 over Q. This term appears when, if I put a Dirac delta function, when this J so just I can write this as, instead of a Kronecker delta, I can write this as a function when J prime is some multiple of Q over R. Right? This is one way of writing the first term. But then I need to take I'll take the modulus square at the end. Plus 1 over QC E minus I 2 pi J prime R1 over Q, the modulus square of this thing. Modulus square of sine square pi J prime R C over Q divided by sine square pi J prime R over Q. And this term appears when Q is not a multiple of, so I can write this as, if I'm clever, I can probably write this as this delta function 1 minus this delta function probably this is how I can write the entire thing, right? G. Oh, sorry. So I take the modulus square of all of this. Got it? So this is the probability distribution. Yes. कोई बात नहीं, लिखने दो. This is a real number anyway. This is a real number. Bracket डाल दो, कोई बात नहीं. No, because this J prime is one of the J's, and so you take the overlap of J with J prime. It's non-zero only when J equals J prime. So J is a sequence from 0 to Q minus 1. J prime is one of those integers. So you're only going to sample out a particular value of J which is equal to J prime. So this is our probability distribution function. Yes, please.
So J prime is one of the terms there, right?
It's hidden. So this J could be ket 0, ket 1, ket 2, ket 3, all the way up to ket Q minus 1. And J prime is one of them. So you want to find out the probability of which J prime is lights up, and only those J primes will light up. Only those J primes will light up where this J prime is some multiple of Q over R. Right? So let's plot this. Let's plot what this probability distribution looks like. In the meantime, you will craft your questions. Alright, so what I'm trying to do now is, I have a state psi 3 on the first register, and I'm going to measure it. And when I measure something in quantum mechanics, I get a probability distribution function, right, of what are the possible outcomes. The probability distribution function is now a function, I'm plotting this as a function of J prime. Now J prime is a variable, is some running variable that can go from 0 all the way up to q minus 1. And for each of these J primes, I'm finding what the probability distribution function looks like. So this is what the probability distribution function looks like. So I will plot this as a function of J prime. Got it? For a given value of Q, R, and so on. So now I don't know R as yet. I don't know R as yet because I want to find out R and I want to use that to compute the prime factors. But if I want to plot this, I need to assume some R if I want to plot it, right? Later I'll tell you how to compute that R from what the probability distribution function looks like. So you do an experiment, R is unknown, you will get a probability distribution function. And from that, somehow you need to distill the value of R from it. But for the time being, what I'm going to show you is what the probability distribution looks like for some value of R. So this has all of these terms. This term lights up, this term becomes prominent. This term becomes prominent only when this thing is non-zero. This is a delta function. Only when the J prime at some value of J prime, which is a multiple of Q over R, does this term become prominent. Otherwise, this term holds sway. This term takes the central role. Now what does this term look like? It's a fraction of 2 sine squared, right? Here's a large frequency function in the numerator because it has a c with it as well. This is without the c. So this term in the denominator is really a function which varies not as fast as the numerator. Right? So if I were just to be slightly more intuitive with trigonometric functions, the numerator looks like a very rapidly squiggling function. And the denominator looks like a slowly squiggling function. And when I divide the two terms, after of course taking the squares, I will just be left with, so I'm dividing by a large number in the middle, I will just be left with peaks at the edges, followed by very small amplitude and then peaks at the edges again. So this is the kind of function that I'm expecting. This is the kind of probability distribution that I'm expecting from this. So, and this term holds sway only at particular values of Q over R. When J prime is some multiple of Q over R. Q over R is a number, 170 for example. So it's only prominent when J prime is 170 or 2 times 170 or 3 times 170 or so on. So let's see what the function looks like. So just giving you some intuition of how all of this works. Sorry, it's a bit technical, but kya kare? Alright, so first of all, is this all visible to you? Chota to nahi font? So I made this mathematical notebook, so if you look at this, at this row here, so what I've done here, just for your convenience, let me make this a bit bigger. So I'm making a sequence of exponents of some number 5, and I'm varying x, the exponent, and you will see that this is a periodic function, right? So the answer for this modular exponent is 1, 5, 4, 20, 16, 17, and then the sequence repeats itself. So the R for this is 6. Alright? So I'm taking my number capital N to be 21, and I'm also, what I'm going to do now is I'm taking 10 qubits in the first register, which means my Q is 1024, my R is 6 because the small a that I'm using I think is 2. This is my Q over R and so on. So let me show you what the sequence looks like. So I need to write this minute. Q is 124. My R is 6. My C is '" This is what the probability distribution function looks like. So I'm going to explain this in a minute. I don't know. All right. On the x-axis, I have my Q prime. My Q prime varies from 0 to 1024. On the y-axis, I have a probability distribution function. I have 10 qubits in my first register. So my Q is 1024. So I have 1024 possible values of Q. The state can collapse. It has a realm of possibilities which has a size of 1024. It can collapse into one of those 1024 states with a certain probability. So this function shows us that probability for each possible value of Q, or sorry, each possible value J prime. And you will observe that it only peaks, it has a peak at certain values. The first peak is at 0. The second peak is at a number 171. Now what is this 171? This 171 is C. It's Q over R. When my J prime equals Q over R, or 2 times Q over R, or thrice of Q over R. Now Q is fixed, 1024. R is fixed for my choice of A. My R is 6. So I take 1024 over 6. I get a number. That is 171. So I will get a peak when if my output is get 171, I will get a peak there in the distribution function. So it's very likely that if I were to run this algorithm, if you look at these results over here, it's very likely that you will either get 0 or get 171 or get 2 times Q over R or get 3 times Q over R, 4 times Q over R, 5 times Q over R. And this is also a periodic function, and the spacing between these probability peaks is Q over R. So after every Q over R, I will get a peak, which means that it's very likely that my outcome, after I've made a measurement and after I've done the inverse quantum Fourier transform, is going to land onto one of these states. Suppose I run a particular experiment and I get this outcome. That is, my output ket J prime is 171. Right? Now this 171 is some multiple of Q over R. From this I need to extract R. But it could be the first multiple, it could be the second multiple, it could be the third multiple. So still I have to do some classical computation in order to extract the period from this. That's what I'm going to show you now. Alright, so any questions about this distribution function? Yes?
What is the peak number at significant
I think this is just a numerical thing. The peak should be equal.
the last peak is
Yes, the last. So,
very, very small.
so that peak is just this peak wrapped over, right? And in fact, if I were to plot each one and want to look at a close-up of each peak, this is what it looks like. This is the sine square, the sharply wiggling peak divided by the softly wiggling peak. This is a close-up of that peak. This is what it looks like. Remember, sine square x, sine square pi x or sine square x. This is what this kind of function looks like. Anyway, what I would like to do now is I would like to come up with an algorithm to find out R from this sequence of peaks. इसका remote now. Oh, sorry. J prime, peak at 0, peak at Q over R, peak at 2Q over R, and so on. They get R peaks. Now, suppose my result is Q over R, this thing. This is my output. My integer output is Q over R. Now, from this I need to extract R, but I really don't know whether it's Q over R or 2Q over R or 3Q over R, right? But so now how do I extract R from this? For this I need to know one small thing. All right. So suppose my output is B. Which is the same as J prime. So get some B, some integer as my output. Now what I would like to do, I would take this b and divide by q. Q is known. This has to be some multiple of 1 over r, right? Now this is my fraction here, right? Of course my b is going to be less than q. So this is a kind of a proper fraction in which the numerator is smaller. Now what I would like to do now is, I would like to take this thing and express this as a continued fraction. Now the classical algorithm starts. Express b over q as a continued fraction. Now let me give you an example of a continued fraction. What does a continued fraction expansion look like? Suppose I have a fraction, say 13 over 25. This is a proper fraction. So let me just put 1 in the numerator. Correct? So now I want to break this up. In the first step I invert. In the second step I take the denominator and split it. I split it into an integer and a fractional part. So this becomes 1 plus 12 over 13. So I invert, then I take the denominator and split it, and then I want to I take this part here and I invert it. So I take 1 over 1 plus I invert this 1 over 13 over 12 and then I split this up again. So I left with 1 over 1 plus 1 over 1 plus 1 over 12. Stop. Terminate. Algorithm terminates it. So this is an example of a continued fraction expansion of 13 over 25. So how do I define a continued fraction expansion? I have some fraction. If I were to express this in this form, b naught, I could also start with improper fractions. But in the general case, I have b naught plus 1 over b1 plus 1 over b2. All of these b's are real numbers, plus 1 over b3 plus 1 over b4, and I can go to wherever I like. Eventually I terminate somewhere, right? So this is a continued fraction expansion of some fraction. Okay? So I've done this for one particular example here. The strategy is divide and conquer. Right? Invert, split, invert, split, invert, split. Put people, you colonize, invert them, split them apart, invert them again, jostle them around, have fun with them, make a mockery of them. But this is what this algorithm looks like. It's a totally classical algorithm. And another definition is that I can define the convergence of this continued fraction expansion. The convergence of a continued fraction expansion R. So the continued fraction expansion can be written in compact form as B naught, B1, B2, B3, some say BZ, right? This is the same as B naught plus 1 over, is it B naught plus, yes. Right? So this thing is written in compact form in this manner. So the convergence of this number, this fraction, are B naught. This is one, the lowest order of conversion. The next convergent is B naught, B1. The next conversion is B naught, B1, B2. The next one is B naught, B1, B2, B3, and so on. So if in that example 13 over 25, the first conversion is 0 because B naught is 0. The second conversion is 1. The next conversion is 13 over 12. Oh, sorry. Yeah. The next conversion is again 1. The final conversion is 1 over 12, right? So these are the conversions of 13 over 25. So now when I have my this number B over Q, where B is my integer that I get as a result of a quantum measurement, and I divide it by Q, I get a fraction. I find the convergence of B over Q. So the next step in the classical part is once you've done a measurement, you get an output B, some integer B, divided by Q, B over Q, find the convergence of B over Q. If my B happens to be 0, there is some finite probability that my output is 0. I just discard that result and rerun my algorithm. Because then I cannot have any, I do not have any chance to find out R. If my R, if B is non-zero, I can proceed. So I find B over Q and then I find the convergence of B over Q. Now I express these convergences in fractional form. Express each conversion as a fraction, and I'll exemplify this in a minute, so don't worry. I express each conversion as a fraction, and then I choose the conversion in which the denominator has the maximum value smaller than capital N. So find the fraction or find the conversion in which the denominator has the maximum value smaller than capital N.
सर वो 12 नहीं होगा 1/12 की बजाय?
क्या नहीं होगा?
12 नहीं होगा, just 12 rather than 1/12.
right? So this is the algorithm for finding R. That's my guess for R. Let me give you an example. Again, let my Q be 1024. Let my B be interest of time. Let my R be 6, my B be 170. So I get an output, get 170. So I take B over Q, which is 170 over 1024. So let's try to find the continued fraction expansion of this. So this is 0 plus actually 6 this is B over Q, which is 0 plus invert plus 1. This is 6 plus I think 4 so this is 1024, right? So 176 are
यही होगा.
यही है
Yes.
1020. So plus 4 over 6, isn't it?
ठीक है फिर 170 times 6 is.
तो यहाँ पे 170 आएगा.
Yes. 170.
ठीक है. Six plus and so on. I can continue this. But the first conversion is 0. The second conversion is 6. It's actually the conversion is 1 over 6. And so on.
We have to continue up to the point where numerator becomes.
Right. So the next one would be
सर 6 ही नहीं होगा खाली.
six plus 4 over 170. नहीं 1 over 6 होगा.
According to the algorithm.
तो देखो ना, first is 0, the other is 0 and a 6. So 0 plus 1 over 6. The conversion is, so this thing is B naught plus 1 over B1.
Because sir, ये भी 1 over 12 होना चाहिए.
चलो वो बात की बात है ना. So this is how we define our convergence. This is the continued fraction expansion of a number. And how do you define the conversion? The conversion is, the first conversion is B naught. So this B naught is simply B naught. B naught B1 is B naught plus 1 over B1. Then B naught B1 B2 is the next conversion. This is B naught plus 1 over B1 plus 1 over B2. So this is the continued fraction expansion form of this conversion. So by this definition, our next conversion is going to be 1 over 6. What's the next conversion going to look like? So in order to do that, we take this 4 over 170, we invert this, 170 over 4. Now if I look at 170 over 4, think this is 42. 8, 10, 2, right? So this becomes 0 plus 1 over 6 plus 1 over 42 plus 2 over 4, 1/2, right? The next conversion would be 1 over 6 plus 1 over 42. The one after that would be 1 over 6 plus 1 over 42 plus 1 over 2. These are all the conversions of 170 over 124. Alright? So now this is already expressed in a nice fractional form. Let's see what this form looks like. If I were to express this as a fractional form, this would become 42. 6 times 42 is 1. क्या होता है 6 times 42? 248. और उसमें यहाँ क्या लिखूँ 250? I don't need to go any further. 253? ऐसे? ठीक है? So now look at all of these conversions. This is the lowest order conversion, the next conversion, the conversion then after, and so on. Now what is the conversion in which the denominator has a maximum value smaller than, I want to factor out the number 21. Six. Right? So now what I would like to do is, I would like to use another concept from number theory, and that is the following. My R is defined such that AR equals 1. Just 3 more minutes, I promise. My AR equals 1 in modular n arithmetic. So I have a guess of R. Right now I have a guess of R. My guess of R is 6. The denominator over there in the conversion in which the denominator has a maximum value smaller than the number I would like to factorize. So this is true because R is the period of this function. So this means AR minus 1 is 0. AR minus 1 is a multiple of n. This really means A. Correct? Now if my small r turns out to be an even number, I proceed. If my small r turns out to be an odd number, I rerun my algorithm with a different choice of A perhaps, because I'm choosing A's randomly. So if luckily my r in this case turns out to be 6. So my r over 2 is 3. Now if each of these numbers is non-zero and neither of them is a multiple of n, then I can go ahead. And what I could then do is that I would then know that my I would take this number, say, so I have to satisfy a few conditions. Neither of these numbers is 0, which means that neither of these numbers on its own is a multiple of n, right? And if that is the case, which is true, then I would take my r, I would take this number, say ARO2 plus 1, and find its highest common factor with my number which I wish to factorize, capital N, and this will give me one of my prime factors. So in this case, my A was 2. I run this algorithm with my A equals 2, so I need to find out the greatest common divisor of 2 raised to power 3 plus 1 with 21. So this is 9 and this is 21. The greatest common factor would be 3. So this is one of the prime factors of 21. The other would be 21 divided by 3, 7. So after you've done the measurement, you run these classical routines, all of these classical routines. It's efficient to do a continued fraction expansion. It's efficient to find out the greatest common divisor because there is an algorithm known from Euclid's times, 2000 years ago. It's called the Euclid's algorithm that helps you find out the highest common factors. All of the other terms are all nice. They're all polynomial, they don't scale exponentially, and the algorithm also is polynomial. So this is how you would find out the prime factors of a number. Now this looks like much ado about nothing. So what's the real point in finding out the prime factors of a number as small as 21? But this is just a demonstration. In fact, the world record these days with quantum computers is finding the prime factors of 21. So because it's really hard to build these quantum computers. So I'll give you some homework problems so that all of these ideas can mesh together. So there's a lot of number theory involved. So I've just passed through this very casually that this cannot be a multiple of n, this cannot be 0, and so on. But there's some deep theory about this. Another point is, why do we have to have twice the number of qubits in the first register than in the first register? What's the success probability?
All right, so m, we choose m, which is generally twice of n. Then we create the state cat 0 on the first m qubits and cat 1 on the second qubit on the second register. So from this point onwards, we do the quantum algorithm, and we precisely do the quantum phase estimation algorithm. So we input this state and we expect that at the end we will get a state which is 2t times 2m times some multiple of q over r. So we take this integer here. So this is going to be some integer close to this value. We divide by 2 raised to power m. We get kq over r. We really get an integer that is close to this. And we then divide this by q to get k over r. We put this equal to our b. And this b will then be expressed as a continuous fraction in this form, b naught plus 1 over b1 plus 1 over b2 plus 1 over b3 all the way up to 1 over bn. And then what we aim to do is we would like to find convergence of b. And the convergence of b will be, of course, b naught, 1 over b1, 1 over sorry, B naught plus B1, then B naught plus 1 over B1 plus 1 over B2, then B naught plus 1 over B1 plus 1 over B2 plus 1 over B3, and so on. So finally, we express all of these convergence in fraction form. We will get some B naught, of course, is an integer, could be 0, then we can RS. So let's not use R. So silly me, let's use some other symbol, say TS, T prime, S prime, T double prime, S double prime. So these are all the convergence of P over Q. And then we choose a particular fraction in which the denominator is the maximum but less than n. That will be our choice of R. Now, if that choice of R is odd, we restart. If this choice of R is even, then we're lucky, because we can then form R over 2, which becomes an integer. And if we are at this stage, what we could do is we could use our initial choice of A and construct AR over 2 plus 1, and also construct AR over 2 minus 1. And if neither of them is 0, which is not possible because AR over 2 plus 1 is equal to 0 really means that AR over 2 is minus 1, which is kind of silly. R is a real number. AR over 2 equals 1 means that R is 0, which is again silly because R is some number greater than 1. So none of these numbers is 0, and none of these numbers is a factor, is some multiple of n. So what we could then do is find the greatest common divisor of AR over 2 plus 1 with n. And if this is not equal to 1 and is some number which is P1, then P1 would be a prime factor of n. And the other prime factor of n, of course, will be n over P1. So this is how we can really use the quantum phase estimation algorithm as an alternative circuit to determine the order of a periodic function. And from the order of the periodic function, we can estimate what the prime factors are. So what we need to learn about is a few things, which I would leave to your kind imagination, is how do we implement use? So what kind of elementary gates are needed to implement use, and are there efficient ways of doing this? And what is the success probability? So this is a probabilistic algorithm. It will fail many times, and it will succeed sometimes. So what is the probability of success? So for both of these points, I would refer you to look at the literature. So this is all that I wanted to discuss about as far as the quantum phase estimation implementation of Shor's factoring is concerned. So inshallah, see you later.